Hello everyone, myself Dr. Pooja Kapoor. I am Assistant Professor of Physics at School of Basic and Applied Sciences, Maharaja Aghasen University, Baddi, Himachal Pradesh. The topic of my presentation for today is half wave and full wave rectifiers. The outline of my presentation is I'll briefly introduce you to the rectifier and the process of rectification, its types, half wave rectifier and full wave rectifier. Further, half wave rectifier is divided into two types: center tap full wave rectifier, bridge full wave rectifier, their features and comparisons. We all know that the electricity which comes to our homes is in the form of AC, but the appliances which we use daily in our day-to-day life are all working on direct current, that is DC. So we need a device which could convert that alternating current which comes to our home into direct current. So this process in which we convert the alternating current into direct current is called rectification. And rectifier is an electronic device that is used to convert alternating current into direct current. The main features of rectifier are it should be simple to use and it should be cheap, cost effective, and third, its efficiency should be high. It should be able to convert most of the AC into DC. It should have a longer life and the process of rectification should be noiseless. So a rectificator fire is basically a PN junction diode which is used to rectify AC. And the type of rectifiers which we are going to study are half wave rectifier and full wave rectifier. The rectifier, we use PN junctions because when we forward bias the PN junction, it conducts the current, and when we reverse bias the PN junction, it does not current. So on basis of this principle, we use PN junction in the form of rectifier. PN junction offers low resistance to the flow of current when it is forward biased and high resistance to the flow of current when it is reverse biased. Current flows through the PN junction when it is forward biased and no current flows when it is reverse biased. So it conducts AC half cycle only when it is forward biased, and so it is able to convert alternating current into direct current. So next is the circuit arrangement for the half wave rectifier. As you all can see here, we have in the diagram, we have a transformer which is here, and we have a PN junction which we are using here, which acts as a rectifier, and the output V0 is obtained across the load resistance RL. So this is the circuit diagram. It has a transformer. As you all can see, the AC is applied to it. The transformer is connected to the diode where the process of rectification occurs. The output is taken across the load resistance RL. The diode conducts for the half cycle only when it is forward biased and does not conduct for the negative half cycle when it is reverse biased. The theory of this circuit is as we apply the AC, with the change in the half cycle of the AC, the polarity changes. During the positive half cycle, the upper end of the coil is positive and the negative end of the coil is negative. Hence, the diode is forward biased, so it conducts. And during the negative half cycle, the upper end of the coil S is negative and the lower end of the coil is positive. Hence, the diode is reverse bias and it does not conduct. So as you all can see, this is the output which we obtained. Here is the input. The AC is applied here. These are the AC half cycles during which we can see that the polarity is changing. We have a positive half cycle and we have a negative half cycle. During the positive half cycle, the diode is conducting. So we are obtaining a current in this case, and during the negative half cycle, the diode does not conduct. So we do not obtain any current during the negative half cycle. So that is how a rectifier works. So next we have full wave rectifiers with us. There are two types of full wave rectifiers. One is center tap full wave rectifier and the second is bridge rectifier. In case of center wave full wave rectifier, we use two diodes in it. In junction diode, current flows only when it is forward biased and is negligible when it is reverse biased. So the diode are conducted in such a way in the case of full wave rectifier that when one diode gets forward biased, the other is reverse biased. So the output is obtained in case of both half cycles of AC. So when we have positive half cycle, one diode conducts, we get the current, and when we have negative half cycle of the AC, the other diode conducts. and we get a continuous supply of DC both in case of positive and negative half cycles of AC. In the circuit diagram, again we have a diode, two diodes D1 and D2, the load resistance RL, and the input AC is again applied across the transformer, and the transformer is connected to the diodes for the process of rectification, and the output is obtained across load resistance RL. This is the circuit diagram. You can see here again that we have a transformer here with us. We have two diodes and the output is obtained here across RL. So in the theory we have that during the positive half cycle, the diode D1 is forward biased, so it conducts, and the diode D2 is reverse biased, so it does not conduct. While during the other half cycle, negative half cycle, diode D1 is reverse biased, so it does not conduct, and diode D2 is forward biased, so it conducts, and output is continuously obtained across load resistance RL. This is the output as you can see in the diagram. During the positive half cycles, diode D1 is conducting, we are obtaining output here, and during the negative half cycle, the diode D2 is conducting. So we get a continuous DC. Here you are getting a continuous DC for the AC, so it is a perfect rectification process is happening where AC is getting continuously converted into the DC, right? So during the full wave rectifier, we can see, and during the positive half cycle, in case of both half cycles, the diodes are conducting and we are getting a continuous supply of DC. But the disadvantage in case of this center tap full wave rectifier is that it is difficult to locate the center tap. Since we are taking the output across the center tap, so it is very difficult to locate the center tap. And these types of in these types of rectifiers, it is difficult sometimes to obtain this type of center tap rectifier. And each diodes can use only half of the rectifier voltage. So we cannot use it for high voltages, and our power supply is getting wasted because we are only able to utilize the half of the power. So to avoid this disadvantage, we next study the bridge wave rectifier. It is mostly used for full wave rectification. In this circuit, we have four diodes with us, D1, D2, D3 and D4, which are connected in the form of a bridge. So when they are connected in the form of a bridge, so this rectifier is now named as bridge rectifier. You can see this diagram. I think it is visible to you all. This is your transformer where you are getting the input AC. Next, it is connected to this rectifier bridge. You can see there are four diodes, D1, D2, D3 and D4. So these diodes, they are forming a bridge. You can see this is a bridge form, and in one case, two diodes conduct, and in the second half cycle, the other two diodes conduct, and we get a continuous supply which we obtain across this load resistance R. So AC supply, which is to be rectified, is inputted to the transformer and is applied to the diagonally opposite ends of the bridge, and the load resistance is applied across the other two ends and output is taken across it. So in the theory we have, during the positive half cycle of AC input, point A is positive and point B is negative. So diodes D2 and D3 are forward biased and they conduct, while D1 and D4 diodes are reverse biased, so they do not conduct. So during the negative half cycle of AC, the input point A is negative and B is positive. So diode D2 and D3 get reverse biased and do not conduct, while D1 and D4 diodes are forward biased and hence they conduct. So whenever diode D2 and D3 conduct, or D1 or D4 conduct, rectifier operates during both positive and negative half cycles and a constant output supply is obtained across RL. This is the output. You can see in the case of positive half cycle, we have diode D2 and D3 are conducting, so we are getting output there. And during the negative half cycle of AC, the diodes D1 and D4 are conducting, so we get an output across them. So whatever may be the case, it is positive half cycle or negative half cycle, we are obtaining a continuous supply of DC. The advantages of this type of rectifier is the center tap transformer is not required, the full voltage of secondary is applied across the two conducting diodes. So output is twice as in previously we obtained in the center tap circuit, and the peak inverse voltage is half that of center tap rectifier. The disadvantages in case of this bridgeway rectifier is that it is uneconomical, it requires 4 diodes, and it has low efficiency. So next are the parameters which we study while we have to categorize these rectifiers. First is peak alternating current. The magnitude of maximum current through the load is known as peak alternating current. Next is DC average current. The average value of output current is obtained by averaging instantaneous value is known as DC or average current. Third is root mean square value of output current, which we call IRMS. It is obtained by taking the square root of average of the DC of its square over the whole cycle. Efficiency of the rectifier, it is defined as the ratio of DC output power to the AC power supplied to the rectifier. Next is ripple factor. It is a very important characteristic. It is the ratio of RMS value of AC component to the DC component in the rectifier. It shows the percentage of AC which still remains present in the DC which we get after rectification. Peak inverse voltage. It is the maximum voltage present across the diode when it is not conducting. So next we present a comparison between these parameters which we obtained in case of half wave rectifier and the full wave rectifier. So you can see the first is peak alternating current IM. In case of half wave rectifier, its value is IM upon RF plus RF. And in case of full wave rectifier, its value is again EM upon RF plus RF. DC alternating current IDC. In case of half wave rectifier, the value is IM upon pi, while in case of full wave rectifier, the value is 2 IM upon pi. So the value in case of full wave rectifier is double that we obtained in case of half wave rectifier. The third is RMS current, IRMS. The value for half wave rectifier is IM upon 2, and for full wave rectifier the value is IM upon under root 2, which is again greater. Maximum efficiency which we obtained in case of half wave rectifier is 40.6, while in case of full wave rectifier the efficiency doubles and it is obtained to be 81.2%. Ripple factor. The ripple factor is very high in case of half wave rectifier. You can see its value is 1.21, and in case of full wave rectifier the value reduces to 0.48, which is very important and very crucial factor. We need this ripple factor to be very low. Peak inverse voltage, the value in case of half wave rectifier is EM, and in case of full wave rectifier the value of peak inverse voltage is 2 EM, which is again the double value we obtain in case of full wave rectifier as we obtained in case of half wave rectifier. So this is all I have for you today. So thanks for your kind attention. Thank you all.